This 10.0 kilogram case starts from rest and slides down the ramp. It loses about 294 joules of gravitational potential energy, but reaches the bottom with only about 194 joules of kinetic energy. Has 100 joules just disappeared? No, energy cannot be created or destroyed. For a system with no energy transferred across its boundary, total energy remains constant, although it can move between stores. Take the case, Earth, and ramp as our system. Friction has increased the internal energy by the missing amount. Near Earth's surface, the change in gravitational potential energy is delta E subscript P equals mgΔh. Delta H is the vertical height change, not the distance along the slope. Only the change matters, so choose a convenient 0. This follows from work. Lift the case vertically at a constant speed and ignoring the other effects. An upward force of magnitude mg acting through delta H does work mgΔh, increasing gravitational potential energy by the same amount. Kinetic energy is E subscript k equals 1/2 mv squared. It depends on speed rather than velocity, and because the speed is squared, kinetic energy cannot be negative. For a constant resultant force along the motion, W subscript resultant equals Fs, which equals MAS. Using v squared minus u squared equals 2as gives half m times the difference between v squared and u squared, the change in kinetic energy. First, make the ramp smooth and neglect air resistance. The case starts from rest, 3.00 meters above the bottom, which we choose as 0. Its initial kinetic energy is 0. E subscript P equals 10.0 multiplied by 9.81 multiplied by 3.00, giving 294 joules. At the bottom, its gravitational potential energy is 0, with no resistive transfer. Initial gravitational potential energy equals the final kinetic energy. 294 equals 1/2 multiplied by 10.0 multiplied by v squared. The speed is 7.67 meters per second. During the descent, the gravitational potential energy bar shrinks as the kinetic energy bar grows, but their sum stays completely fixed. The calculation did not need the ramp angle, slope distance, acceleration, or time. The mass also cancels. In this ideal model, objects released from the same vertical height each reach the same speed. But mgh equals 1/2 mv squared is only a special case. It works because the case starts from rest, finishes at 0 gravitational potential energy, and has no other transfer. Otherwise, you need to write the full energy account out. Now let's say that the ramp is rough. The vertical drop is still 3.00 meters, but the distance along the ramp is 5.00 meters. A constant 20.0 Newton resistance acts in the opposite direction to the motion. We still neglect air resistance as sound, but we model this resistance as a friction. The gravitational potential energy decrease is unchanged because it depends on vertical height alone. Work done against the resistance uses distance along the path. 20.0 multiplied by 5.00 gives 100 joules. The work done by the resistance is negative 100 joules. Equivalently, enter positive 100 joules as the work done against the resistance. Choose one convention and don't end up counting the transfer twice. At the bottom, 100 joules has increased internal energy, leaving about 194 joules of kinetic energy left. 1/2 multiplied by 10.0 multiplied by v squared equals 194. So the speed is 6.23 meters per second. The case is slower, but the conservation still holds. In this example, kinetic plus gravitational potential energy has decreased. The total energy of the chosen system, however, is still unchanged. The internal energy increase completes the account. In an exam, choose the system, the initial and final states, and the 0 level. List every energy store and every energy transfer. Then write the energy equation before using numbers. Use vertical height in the formula mgΔh, and then use path distance in Fs. Never describe energy as simply lost, it's just been transferred somewhere else. This overview completes mechanics. Next we begin materials with density and Hooke's law.